So we are now recording. Audio's on. Let's take a look at bright space here. We can see that for the course 365 content, right? We are this week we covered the module perform KNN. Sorry, so I went over the lecture, the Euclidean distance. I assigned a homework, and you got the code here. So if you click on this link, it'll take you to the GitHub where you can find all the code related to this. So that's going to be these two KNN, and then also Euclidean, this one over here. All right, so that is completed module. Let's go back to Brightspace. Today, we're actually looking at a really nice tool, and just various things actually. So this is a module for today, performance metrics. Okay, so this has an explanation, right? So there's a theory that goes with this. There's also some Python code that I usually call the main ML. And we'll discuss several things, including reading in a text file from, a text file from your desktop where you have some data. And then I'll introduce the concept of WEKA here. So let me just, all right. So the first thing we're going to need, obviously, is a data set. So let's go ahead and open up this one. So you should be seeing web course website. Go to Machine Learning Foundations, right? And under here, there should be a couple of data sets. Yeah, there it is. Fischers Iris. Okay, so we're going to need that one. For today. So let's see. Okay. So let's go ahead here and download this file. So this is the file, Fischers Iris. So you can see I clicked on it. It is a CSV file. So just go ahead and download it to your desktop. To your downloads folder. Then move it to the file where you have been storing your all your files for this class. 365 in my case. So there is iris.csv. Okay. So you probably didn't see it. Here I am. I copied the file into the folder. Okay. So now, as you can see, this is a .csv file. So I'm going to just right click on it, edit with Notepad++. And we have to understand something about the data. So in the NumPy example or examples, you learned that you learn how to create data in a matrix form. And if you notice, this sort of follows a matrix form, but it's got words in it and things like that. Okay, so let me switch over to the whiteboard. Let's just think about what this looks like. All right, so the Iris data set, it's called Fischers Iris because it was created by a man named Fischer, who was one of the first people to do this type of data analysis many, many years ago. So Fischers Iris is just like any other matrix for machine learning. It's got samples. In fact, it's got 150 samples. Okay, and it's got 5 columns, The last one is usually the class or label. And then the other four are the features that represent the sample. So feature 1, feature 2, feature 3, feature 4, okay? And you saw the data there for a second. So what do these represent? These actually represent 3 types of plants. The classes or labels are Setosa, Virginica, and versicolor. Okay, so these are the 3 types of classes. It's a 3-class problem for this one. Okay, so usually they're represented by 1, 1, 1, 2, 2, 2, 3, 3, 3. That's how they need to be represented in the code, but excuse me. Usually in some files, they'll be represented as words, okay? So if they are represented as text like this, if you're bringing this into Python, you're gonna have to change it into a number first because NumPy will not handle strings, okay? Now, the program that we're gonna use today, WEKA, supports taking in data like that, and then it just does the conversion for you. Another thing that this CSV file includes is the actual header. And a lot of CSVs actually include the header, okay? And it's something that then we have to get rid of, okay? So that's one of the main ideas there is that we have to get rid of it, but it's helpful to know. So the information about the plants, these 4 pieces of information have to do with petal width, petal length, and so maybe that is actually in the file itself. So you can see how that can be useful. Yeah, so sepal length, sepal width, petal length, petal width. I don't know much about plants, but I know what a petal is. And so petal length, petal width, something to do with the leaves, right? So, and based on this information, you know, people that study plants or, you know, fungi or other kinds of, you know, things from vegetation have a tendency to classify everything into groups. And they do it by the characteristics of the plant itself. So this gives us now a very nice, you know, Iris is like the classic first data set that every data science student will study. All right, it's very simple to grasp your mind around it. Whereas if we used, you know, another very large data set, the problem would be that you would not be able to, you know, visualize it so well because it's so large. Okay, does this make sense, guys? Are there any questions so far? Questions so far? No? All right. So let's continue then. All right, so we've got the file. Now we have it in here. Notice that the values are like 5.1, 3.5, 1.4, 0.2. In the next row is 4.9, 3.0, 1.4, 0.2, and so on, right? So these are the values that you have in each column of the Iris data set. All right, so this file we will need to process today. All right, so this file we will need to process today. So there's a couple of ways that we can process. So as I said, one of the first things I want to show you today is just this tool WEKA. Okay, so let's do WEKA first, okay? Now, what is WEKA? So the first thing, I think I have a link to it. I hope I do. All right, yeah. So I click on WEKA here. And it is a nice program developed, you know, at least 20 years ago, I think. It's developed in New Zealand by a university over there. And it's pretty good. It's got a lot of documentation and definitely worth having in your toolkit. You can download it easily for Windows, so it's free. So go ahead and download it. It's supposed deep learning even. So, you know, they're constantly updating this. So let's go ahead. I have it over here. So I'm going to just start it up. You know, type WEKA, click on it. I'm going to have to share the computer here. So you can see it opens up a window like this. It says the first window says WEKA has a package manager that you can use to install many learning schemes and tools. So what that means is that it's got so much stuff, in fact, that some people may not want to use all of it. So the idea is that you just download the kind of like the basic stuff, the default version of it. And then through the package manager, you can update and download the rest. Okay, you can download the rest. So I'm going to click OK here. We're just going to use the very basic install right now, but you guys can explore the rest if you want. So you should be seeing me navigating through WEKA. It's just this little window here. Okay. And so it's got basically, so you guys are following along, correct? All right, so it's got basically these 5 buttons that allow you to do different things. So usually the one I like to use the most is Explorer. Because this tool is basically, as I said, it's a nice tool for data exploration. Depending on the size of your system, it can handle actually a lot of data. Not big data, per se, not millions of records, but certainly a lot of data, 100,000 or so. It also has some settings in the files, in the installation files, where you can increase the amount of RAM. So like if you have 8 RAM, you can, you know, I think by default, the RAM that's allocated to WEKA is like 1 gigabyte or something. But if you have 8, you can raise it up to 6. So I used to, you know, always raise it up to 6. Nowadays, if you have 16 gigs of RAM, then, you know, that's even more. Okay, so hopefully that makes sense. So memory, certainly when you're dealing with machine learning, is an issue to deal with. The experimenter is another nice one. It allows you to do what is called a t-test. So the t-test, you know, when you took your statistics class, I'm sure you learn about probabilities and then, you know, p-tests and t-tests and all that, p-values. So, you know, here, whenever let's say that we have 3 classifiers that we are comparing, right? We're comparing 3 classifiers. So, you know, we're going to get some results that say that one classifier has an accuracy that's higher than the other. It's all about performance, you know, how it predicts how well. But statistically, saying that something is better than something else just by one experiment is not the same as saying that something is better than something else. And by the way, that the result is statistically significant. Okay, so what that does, which is pretty good, is that experimenter allows you to do like statistical tests to actually know for sure, yes, this is definitely better than this method, you know, KNN is better than naive Bayes for sure, okay? And so we'll look at this. I'll come back to WEKA later when we look at the t-test for machine learning, okay? I'm also gonna implement that in Python, but it'll be good to have that as well. All right, so that's what the experimenter is for. The other ones, this is a command line version of it. This is an extremely GUI focused version of it where you can just like drag and drop icons. I would recommend you stay away from that. as I don't want to point you in that direction. Okay, the problem with those GUI grab and things is that the more you end up with that, the more people are going to start charging you money for those kinds of things when you can actually do everything for free. Okay, so don't get into that habit. It's a bad habit. All right. So anyway, let's look at the Explorer. I'm sure this is what you guys want to see. So how does it work? So as you can see, I opened up another window by clicking on Explorer, and you should be seeing it now, I believe. So this is how it works. It basically has these tabs over here, okay? And then these tabs allow you to do things. Pre-process just basically means, it's basically like the pipeline. So if you think about it, pre-process just means, dealing with the data, processing it, modifying. Okay, then we have classifier, which is basically what we will be doing all semester, like we classify data on Monday. On Monday, right? We classified some of that data, and I showed you guys we were getting that ones or zeros. Clustering is another technique when you don't have labels. We'll talk about this later, so don't worry about it for now. But these two you certainly should worry about, or not worry about, but focus on. And then we're also going to look at something really nice, which is called the select attributes. So I'll kind of explain what that is. But this is actually extremely useful and powerful, especially for like scientists. Scientists, and what I mean by scientists is like data science is a science, but I mean scientists like if you're a marine biologist, or you're a fungi expert, or you're a plant botanist, you care more about the features in your plants and your botany and your animals than you do about other things. So select attributes allows you to identify things about the characteristics of your samples based on machine learning. And so we'll take a look at that. We'll talk about one of the algorithms underlying feature ranking. There's actually a couple, the chi-square and information gain. So we'll take a look at that. But that's basically the idea, okay? So again, the important thing is these tabs. Now notice that the tabs are currently not highlighted. Now I want to stress another thing. WEKA is not a tool that we will use, that I will focus on all semester. In fact, today's lecture is the only lecture where I will probably cover WEKA, except for when we come back for the t-test, right? Which will be another lecture. So that's it. Out of the whole semester, we'll just spend that. But that being said, it's so easy that you should always in the background be using, okay? Now you will mostly be using Python, but this is definitely a tool that, whenever I have a data set, and I have it ready, boom, I just throw it on this. Even if it's a large data set, what I usually do is on a random basis, I subsample it. Let's say I have 2 million samples, that's a lot of data. And I just say, you know what, I'm going to subsample 100,000 randomly out of this data set just to kind of, and then I'm going to throw it in here into WEKA and just get a feel for it. And then, I'll be like, all right, here's some insight. And then after that, it allows me to kind of point my direction as to, maybe or maybe not, but, it's definitely helpful. Now, to open a file, you have these links here, or these buttons, I guess. Obviously, one just says open file, open from URL, open from a database, or generate data. All right. So in our case, you saw me generate artificial data in NumPy on Monday. But today we are actually focusing on loading the Iris data set at least. Now, additionally over here, if you look, there's these filters. And with these filters, there's a lot of them in there. And what the filters do is they process the data. So the filters are under the pre-process. So for instance, let's say that you have a whole bunch of numbers and they're basic, or maybe you have a column that is numbers, but currently the data type is set to string. So then you can change it to a numeric. You can change something from being a numeric to a categorical, which is nominal, and so on. You can do other things later on in the semester. We're going to do something called singular value decomposition, principal component analysis, or compression. And you can do all that here for sure. So just be aware that this is where you would do a lot, anything of transforming, your original raw data into better data for processing and getting better results. Once you reach your machine learning classifier, you can find here in this filter, okay? Are there any questions so far? Making sense? All right, so I think you guys can hear me. All right, let me just grab some coffee. Sorry, it's just my throat just gets really messed up right now. All right. Anyway, so let's continue. So we have here, once we load the data set, we have these three windows, this one, and this one, and actually this one, so 4. When we load the data set, we will actually see a lot of things about the data set, okay? And so let's go ahead and do this now. So I'm gonna click on open. I'm gonna go to desktop over here. On desktop. You have to change the data type here. ARF is by definition the native data type for WEKA, but let's just switch it to all. Okay. And I'm not sure why. Oh, there it is. All right, and then over here, let's look at, here it is, 365. And then there's the data set right there, Iris CSV. Notice it has to be all files, because if by default, this is a common question I get, I can't find my file, is it an ARF file? No, it's a CSV, so all files. Click on it. Now, by default, it'll load CSV files, okay? You can see here, it's got a lot of information. Instances, there's 150 of them. 5 attributes, because there's 4 features in one class, so that's 4 plus 1 is 5. Then you have over here the features, the actual features. Notice if I click on them, the values over here are going to change. Notice how that works. Notice. Now, importantly, whenever I click on one of these columns, it also gives me the distribution of the data, right? How many samples? So for instance, there are 3 classes of species, and each one has 50. And also, if you look over here, the species column has a data type of nominal. This is, and I want to stress this, this is really important. Usually, this value by default in a lot of data sets becomes numeric. When this value is numeric, WEKA thinks that this is a regression problem, not a classification problem. When that happens, classify over here does not work. The algorithms do not show highlighted as they do here now. These are going to be like blanked out a little. All right. So that's usually because the label, the target label, the class here is numeric. Sometimes also it doesn't know which one's the class, so you have to tell it. Okay. But that's important. In our case, because Iris is so standard, it's actually set correctly, and it interprets it as nominal. Notice that the classes are Setosa, Virginica, Versicolor, 50 of each, right? And you can see the distribution here. If we look at one of the other features, sepal length, you can see there a histogram of the data for it, okay? And then over here, it gives you some statistics about the minimum, the maximum value in there. Okay. And the mean and the standard deviation of it. Okay. So, you know, it took basically the data for that column. It found the mean and the standard deviation, the minimum and the maximum, and then it's trying to plot it. Okay. You know, you can click on visualize all, right? And then and then really quickly, it starts to give you a sense of what your data looks like. Some people, we have a class. So I want to stress this. We have a course so if you guys are taking this course and you've taken the statistics course and you have to take the 265 course, you have 3 out of 5 courses to get the minor in data science. You just need to take the other 2 courses, which are more advanced, which one of them is the visualization course. So that course is like this. So if you like something like this, where you would always plot graphs and charts and little pretty things, and then view it, you know, that's great, right? So that's the visualization course. It's you know, visualization for data science. I cover in one of the grad classes, when I cover one of the algorithms for the attention mechanism, I will also do a little bit of visualization, but in general, I don't do much of it. Okay, but we do have a course just for that. And then just for completion, the 5th course is Professor Taehoon Kim's parallel computing, which he will show you how to use Hadoop and Spark on a and cluster computing. But that's on the CPU basis. So anyway, that's let me close this. All right. So now that we have the data set, we've looked at it over here. Now we know that the class is this one, and we know that it is nominal. So now we really don't have to do any pre-processing. However, let's say that this said that this was numeric instead of nominal, right? Then what do? So what you do is you have to figure out what the number is for the class that you want to change. So species in this case is number 5. That's the index. So you go here to choose, click on choose, and you can see it opens up this window of filters. You have to pick, this is going to be unsupervised. Click on that, and then it's going to be attributes, and then scroll down over here. You can see there's a lot of filters, and you should find one that says numeric to nominal, this one. So then you would click on numeric to nominal. Notice that it is selected now. And then if you click anywhere in the white space here of numeric to nominal, you should be able to see a dialog for setting parameters. So I'm going to click on that. And now you can see here the attribute indices. Instead of applying it to all, you only apply it to 5. Because 5 is the ID for species. And that's it. So then you would hit OK, and then you would hit apply. I'm not going to hit apply because it's already nominal, but you would hit apply, and then this would change from numeric to nominal. So believe me, later in the semester, you will have data sets that will be numeric instead of nominal for the class, and you'll have to do this. Did that make sense? Are there any questions about that? No questions. All right, great. So it's making sense. All right, perfect. So now that we have it, let's do some machine. So we're done with the pre-processing for now. Let's do some machine learning. So now you click on classify, and you can see here in classify. Now, what's important about this is it'll motivate what we're doing. Whenever you do machine learning, you have to measure performance always. And I don't mean performance of how fast a computer is, although that's important. Performance is also sometimes called benchmarking. So you benchmark a very, one fun thing about machine learning is that it's all about competition, okay? So machine learning is very much competition. So that what that means is there's a lot of conferences out there, and then they have what are called challenges. So they'll create data sets, and then you go in and you throw everything that you got at those data sets, and then they need to have ways of measuring performance. So there's a lot of metrics. There's in this course, we'll cover about 6 or 7 metrics, but there are like 30 that I won't cover because a lot of those are specific to the problem. For instance, there is the classic language translation problem. You know, translate from any language to any language. So you guys probably have seen that Google now translates. If I go on Instagram and I find a nice, interesting post, but it's written in, I don't know, Portuguese or something like that, and I want to understand what it, you know, I can spot some words, but you know, if I really want to understand, hit translate, right? And all of that is done automatically. And so there's metrics. That one is called the BLEU score, the blue score. And there's a bit of complication, and it's actually very important. The metrics are extremely important. And so this is central to all machine learning, is measuring performance, okay? So that's what we're gonna do today, but just with the very basics that apply to just classification problems. The classification problem is the one where you have one label annotated and then you predict another label. So, you know, in our case here, we're going to look at plants, samples of plants with their sepal width, sepal length, and so on, those 4 features. And then we are going to predict whether it's a plant called Virginica, or it's a plant called Setosa, or it's a plant called versicolor, okay? All right, so we're ready. So first thing we need to look at is this part over here, the testing options. So whenever you do machine learning, you're gonna train your model on a set of data, and then you're gonna apply that model to another set of data, a subset. But both data sets, the trained data set and the test data set, should not overlap, okay? If they overlap, you're cheating, right? That's not fun. So think, I always give this example. Think of a competition where you're gonna win $1 million, okay? So they give you a data set, boom, train your model, but then they held out another data set which you've never seen. The samples are from obviously similar, but they're not the exact same ones, right? So they're, you know, pictures of cats, but these are some pictures of cats. These are other pictures of cats you never saw in, you know, that picture of a cat in the train set. And so that's the idea with machine learning. And so you're going to train a model and then apply it to the test set, okay? So in all of machine learning, supervised learning in particular, like we're trying to do right now, we're going to do that. So here there are two approaches that we can take, or actually 3. Although there are 4, what are these called? These button things. There are 3 options really. One is the one that's currently highlighted. Cross-validation. Cross-validation, it means it's gonna repeat the process 10 times. So it's not just gonna do it once, it does it 10 times. Each time it divides the data set randomly into 10 bins. It'll take 9 of the bins to train and leave 1 out for testing. Then the next iteration, it grabs the next bin for testing and the other 9 for training, and so on. It does that 10 times. So this one provides more accurate results because you're doing it 10 times randomly on the data. And so that's a good thing. This one is like the easiest. This is only 1 time, and you can just set up the split. So 80%, for instance, or 70%, whatever you want. So what that means is you're going to take your data set. You're going to take your data set and you're going to split it into 70% for training, 20% for testing. So let me ask you this question. So if I do what was there already, 66%, right? Let me actually, so that's 66% is 2/3 of the data, right? So I'm going to ask you this question. How many samples in the train set? How many samples in the test set? Let's see if you're paying attention. That's right, because there's 150, 100 for training, 50 for testing. Perfect, good answer. Usually that's a lot for testing and not enough for training. You always want to give training, you know, a little bit. So 70 to 80, I'm just going to give it 70. All right. Now you can click on more options, and there's certainly more options here, like printing out the labels, etc. You can, you know, it's just point and click, pick those. Now, one important one is this one, num species. You want to identify the class. So you have 4 features and you're using them to predict a specific class. So in this case, if you do this, obviously it's going to be species. It already knows it's species, but sometimes it doesn't. And so you have to set it up. Okay. So click on species over there. And that's kind of it. But are we forgetting something? What do you think we're forgetting? So we did the split. We selected the species. We want to do some classification. What do you think? What else do you think we should do? What do you guys think? We have a training set, right? We by doing the 70% split, we've identified the train set randomly out of the 150. 70% will be allocated to train, 30% allocated to test. What else do we need to define? What do you guys think? So which machine learning algorithm are we using? Or let me rephrase that. Which machine learning algorithm would you recommend I use first? Yeah, which one? Recommend one. Ah, there we go. Why not KNN? Good answer, right? It's the only one you know. So why not? It's an easy answer. I know one, that's the one. All right, so now here, actually, there's a lot of classifiers. So I'm going to click on this. Now, some of these classifiers are not yet installed. Remember what I said, when you first load this, you have to kind of install whatever algorithms you want, okay? So not all of them are there. So for instance, if I click on functions, you can see that not all of these are there, okay? You know, not all of them are available. You see that here? Not all of them are available, so you can add more. But WEKA does come with a few of the basic ones. As I said initially, the first 3 traditional algorithms that we will study this semester are KNN, naive Bayes, and decision trees. So let's find those 3. So KNN is at what is called a lazy. So we click on lazy here, and it's actually this one, IBK. So if I click on that, IBK over here, right? That is the algorithm, basically, the KNN algorithm. You know, you can see that about is the K nearest neighbors classifier, KNN, and so on. Okay. So KNN over here that's one. Then we have naive Bayes. It's this one under Bayes and naive Bayes. You can see that there. You can click on the white space. Class for a naive Bayes classifier using estimated classes. So it's a naive Bayes algorithm. We will learn this later in the semester. This is a family of classifiers which are probabilistic, so they're an important topic in themselves. And then the other one I mentioned is the trees. So I'm going to click on this, and you can see down here trees, and J48 is actually the decision tree. So if I click on it and then you click on this, oops, you can see a prune or unpruned C4. It's a decision tree. I'll also cover this one later in the semester. Within trees, there's also a random forest. So if you have a tree, then if you have a forest, then the forest is probably a classifier that uses several trees to perform classification. Usually when a problem does well with decision trees, it'll probably do better, a little bit better with random forests. It's just like, very likely that that's going to occur. But additionally, there are, of course, other algorithms in here, not just these three. There's also some of the family of algorithms that we will cover in the second half of the semester related to the multi-layer perceptron. So the multi-layer perceptron, I'm sure you guys have heard of neural networks. That's a very common term. Neural networks are the focus of the second half of the semester, all the way up to deep learning, okay? The multi-layer perceptron is in fact a neural net with one hidden layer. So it is not deep, but it just needs one more layer and it would become a deep neural network. Now, the problem with multi-layer perceptron on WEKA with really large data sets is that it's very slow. So I always assign a homework and I ask you to do multi-layer perceptron with a large data set, and everybody just, it takes them a long time to process. And it's really the goal of it is to kind of show you that it's pretty slow here. And that's why we have to use other tools in Python that are designed specifically for being efficient with large data sets. Does this make sense, guys? But for Iris, which is only 150 samples, multi-layer perceptron will be really fast. All right, so let's go ahead now and run it. So I'm going to start with naive Bayes. All right, naive Bayes, and I'm going to select naive Bayes here. Now I've selected 70%. There's the class, so all you have to do is click on the start button. All of these are going to be fast. It's just when you do large data sets in WEKA with multi-layer perceptron, it'll definitely be slower than doing it in Python. All right, so I'm going to hit start here, and there it is. Notice it finished almost immediately. The little bird here kind of starts like moving when it's processing. Once it finishes, it just rests like that. It also gives you a status of okay, so you know it finished correctly. All right. So now we get to the motivation for what we're discussing today, which is the performance. So here, remember, we split the data into 70% for training, 30% for testing, and now we're evaluating our model on that 30%. So basically what we're saying is, I trained a model with naive Bayes on this data, applied it to this other data, and this is how well it did. All right, so there's a couple of things we can look at. We can look at this top score, which kind of summarizes everything. So it says 95% accuracy, right? So it means that out of all the samples that it tried to classify with the trained model, 95% of them were correctly classified. However, accuracy is not always the greatest, especially when you don't have a balanced data set. This data set is balanced. You saw we had 50 of one class, 50 of the other, 50 of the other. So it's a highly balanced data set. And so accuracy is good enough for that. But in other problems, in most real world problems, actually, you're not going to have such a balanced data set, unfortunately. So other metrics are necessary. So the other metrics, you can see them here. Precision, recall, F measure, okay? There's also this one called the ROC area or the ROC curve. Notice that here we get a table of the score per class. This is very useful to have. So what this means is for all the ones that were Setosa, this is the score. For all the ones that were versicolor, this is the score. For all the ones that were Virginica, this is the score. And then this last one is for all. So the average of all, right? So all of it. Now notice here, if we analyze the data, let's start with precision, the first column. We can see that basically 100%, 88% precision for versicolor. So it had a little bit of trouble with the precision in versicolor. Now you might ask, so what is precision, recall, F measure? You know, what's the meaning of that? We will see that in the slides. Okay, so we'll come back to that in the slides to get a feel for how that works. But for now, let's just focus on reading this data. So we can see precision was not the greatest for versicolor. Then we had precision for Virginica, which is 100%. And then on average, the precision is 96%. Okay. Any questions so far? No questions. All right, let's look at the next one, recall. Notice that in the recall, Setosa and versicolor are actually pretty good, and now it had trouble with Virginica. Virginica is 86%, all right, with naive A's. So that, you know, there's some issue there. Now, F measure is usually a metric that combines precision and recall in what is called the harmonic mean of them. And it basically says, you know, instead of looking at precision and recall specifically, look at F measure. And actually, F measure is the metric. If you can only look at one metric out of accuracy, precision, and recall, look at the F measure, okay? Just look at that one. It'll give you in one score, it'll give you the best indication of how your model does. It's like, it gives you the best of all worlds, if you want to put it that way. So now let's take a look. The F measure is 100 for Setosa, 94% for versicolor, 92% for Virginica, and overall it's 95%. So 95% accuracy, by the way, is extremely good. I actually think this way. Whenever you do something in machine learning, and you get scores that are above 90, it tells me that the problem is very easy, okay? Because usually it's really hard, actually, to get things to work. And so when scores are this good, it's basically because it's a data set like this one, a highly studied data set. You know, people have already found all the optimal things about it, okay? Make sense, guys? All right, so those are the metrics. One fun one is the confusion matrix. I really like that one because the confusion matrix actually tells you where it misclassified. So for instance, you can see here, what you want to see is the diagonal having all the values and everything off diagonal to be a 0. It means basically in one quick look, you can see that the algorithm it performed really well. But if you start seeing values off the diagonal, like this one here, then that's an error. So the way to interpret this is, let's say, out of all Setosa in the test set, 14 were classified. Well, Setosa is A. So all 14 were classified as A, and 0 were classified as B and C. So that basically means there were no errors. If we look at versicolor, out of versicolor B, all 16 were classified in B, so no misclassifications. But if we look at Virginica, for the test set, what do we see? Out of 15, only 13, with, you know, in Virginica being C, only 13 were classified as C, 2 were incorrectly classified as B. So those are 2 errors which account for the errors in the that we see here. So as you can see, this is very useful. Obviously, when you have more data, when you have more data, there's going to be more things or more labels, etc., for you to interpret. Okay. All right. So that's the interpretation. So if you look, there were 5 metrics that we looked at: accuracy, precision, recall, F measure, the confusion matrix, and there are others like the ROC curve. I'm not going to cover that right now. All right. So I did naive Bayes, but you might ask the question, is that the best classifier? Well, let's see. One thing about naive Bayes is that it is usually the fastest. Naive Bayes is a fast algorithm. And actually, by definite, and usually, as you might think, since it's fast, it's probably not as accurate. And it's usually true that naive Bayes is always the fastest, but you might, if you use other algorithms, those algorithms may get better performance. So what I like to do is when if I have some data, I can apply naive Bayes to it. And by applying it really quickly, it gives me a benchmark so that I know, okay, at least it'll do this well, but maybe even better. So then I can think of where I am in the problem that I'm trying to deal with, if that makes sense. Okay, so that's the idea. Okay, so let's try another one. So remember the 4 that we're going to try today. So we tried naive Bayes. Now I'm going to try KNN, right? KNN. Right, so I'm going to click on KNN over here. Species is selected. Set it 70% split. Notice what's going to happen is the data for naive Bayes is this entry. Now it's going to add a second entry for IBK, which is the KNN. So I'm going to do start. You can see it finished already. And now you have the IBK data. So now if you click on both of them, see how the values change because it is switching from one to the other. Let's take a look at IBK. Now for this problem, they're practically the same. You see that? They're practically the same. There was almost no change whatsoever. So what that tells you is that they actually do pretty well. Let's try another one. Let's try a decision tree. So J48, let's try that one. All right, this one's done too. Basically, same results. No real improvement, and that's just because the nature of this one. Let's try our random forest. And the same results, right? So there's almost no change in this. We need a more complex data set to be able to see more differences. But for now, at least you know how to run 4 classifiers, okay? Another thing is sometimes you have 2 data sets. You have a trained set and a test set, right? So in that case, you have to load one and the other. So let's go to the right space environment. And if we look, we have these 2 data sets, MNIST train, MNIST test. So you should be seeing the website. So in the course website, right, we have 2 data sets, MNIST train, MNIST test. So I'm going to download them. Have them now. So let me just copy them to my desktop folder. And actually, one of these is downloading because it's big. So just give me a second. Grab some coffee while it's downloading. All right, so I think it finished downloading. So I'm going to copy these two files from my downloads into the desktop. All right, now these are large, I believe. So if I switch back to this, now you should be seeing MNIST test, MNIST train. You can see if you compare the size, look, Iris CSV is about 4 KB. MNIST test is 17,000 KB. And MNIST train is 107,000. So much larger, right? So let's go ahead and switch over to WEKA. Okay. So now what I'm going to do, I'm just going to close this. I'd rather start all over. I click on Explorer. And now the goal will be to load up the training set. Now I have two separate files, so I have to deal with them separately. So let's do open file. Let's, navigate where I have them on the desktop, and I have them here. And then, of course, the ARF, set it to all. Okay, so my files are in here. I want to load train set. Notice down here it's saying reading from file. There we go. Now we've got our data. Remember, we're going to explore it, and let's see. I look at here, it says 60,000. So there are 60,000 training samples. It's got 785 attributes. Out of those, 784 are features. And notice that now it's not the first one, or sorry, it's not the last one, but the first one is the label. See that? And if I look at it, the label is numeric. Problem, right? So, because we want to do classification, so we have to convert it to nominal. Another thing that's recommended when you're dealing with train and test data is to actually change the format from CSV to ARF, the native data format for WEKA. Just WEKA wants it that way, so it's recommended to do that. All right, so let's take a look then at our data. We can look at all the features, right? You can analyze all the features, provides all their values here. Now, MNIST, I should say, is the famous handwritten digits data set. So what we're looking at here is we're looking at images. Okay, so if I go over here, MNIST is the famous data set. Train probably has 10,000 samples. We'll see. We'll double check. No, sorry. Train has 60,000. And then test has about 10,000. Now, every sample in this picture, in this data set is like this. So we've got X over here, we've got Y. There are, for the train set, there will be sample 1, sample 2, all the way to sample 60,000. And there will be all the way to 784 features. Now, why 784 for each row? It's because of the following. Each row is an image, and the images are small images of size 28 by 28. So that is 28 pixels, okay, by 28 pixels. And they're black and white, so there's no RGB. So it's not like, you know, RGB for color images. Instead, they're just black and white, and they're just of handwritten digits. So people did this, right? That's my 8. But in another image, you know, some of you might, you know, I don't know, do an 8 like that. Probably not. But, and then someone else might do like that. And, you know, notice other numbers, for instance, are more obvious. Like, for instance, 2s. Some people draw 2s like that. Notice that I actually draw them like that. And so, you know, it basically has this. It has all these handwritten digits of all the numbers. So from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are, so what you're trying to do is, given the image 7, you want to predict that it is, in fact, a 7. So this is a 10 class problem. Do you guys see that? This is a 10 class problem. Does this make sense, guys? All right, so let's go back then to WEKA and fix a few of the problems. So the first thing I want to do is just fix up the, I want to fix I want to fix the, let me just make sure I'm sharing right. The label. So the label is this one, and it is currently numeric. So that's the first thing I'm going to try to change. So that's 1, index 1 over here. So I'm going to click on choose. I'm going to click on filters. I'm going to click on supervise. I'm going to click on instance. No, sorry, not instance, attribute. And I'm going to hit numeric to nominal. And then I'm going to select label ID1. Going to be 1 over here. And now I'm going to hit OK. And now I'm going to hit apply. So if you notice, the little bird was thinking there, but now it finished. We click on the label. We look at it and notice that now it says none. All right, so that's very important there. Everything else should be fine. So if we look and notice also the distribution of the data, right? So it's not exactly balanced perfectly, but it is balanced. There are roughly about 5,000 of each of the 10 classes. So notice that there are 10 labels, 10. And so we've got some of our data here. Click on the other ones, these should be numeric, should be fine. Notice that not all pixels have values, right? Because some are just white space in the background. But this one that I click randomly does have values, okay? So now that I have this, the next thing I'm going to do is I'm going to save this as an ARF file instead of a CSV. So I'm going to, since I already processed it, I'm going to click save in my same folder, and I'm just going to say that it's a file type ARF. I'm going to click save, and that should be it. My data now should be ready to go as an ARF file. So let's double check on that one. I'm going to go to the folder, and you can see mnistrain.csv.arf. So now it's a ARF data type. Now let's do the same for the test set. Let's go back to WEKA. All right, so you should be seeing this. Now we're gonna open up the test set. Make sure you select all files. And now we're looking for MNIST test CSV. Load it up. There it is. Okay, this one, if you look, it's got 10,000 samples, right? And Now we're going to look for the label. There it is, the label. Same problem. It's numeric. We have to change it to nominal. So I'm going to go ahead, same process. Click on choose. Scroll down to numeric to nominal. Oops. Numeric to nominal. It's the first one. So I'm going to click on this. Select the first one. Click OK. Apply. Now, if we look at the label, you can see it is now nominal. We can see the labels there as well. It's balanced. And now we can just go ahead and save it as an R file. So mthistest.arf. Let's save it. Go back to the folder. And you can see now we've got both the train and the test as R files. They've been processed. They're ready to go. So now let's go ahead and so now what I'm going to do, since I've processed them, I usually just close this up. So I'm going to close this window. And then now I'm going to load the process data to do the machine learning analysis. So now I'm going to do Explorer. Then I'm going to open the file. This time, I want the train data, but I have to load it in a different way now. So I'm going to go to the folder, 365. I got my two files here. So load train. There it is. I got train now. It's nominal. So now, since it's ready to go, I'm going to switch over to classify. I'm going to click classify here. Notice that now I'm not going to use cross-validation or percentage split because I have two data sets, the train and the test separate. So instead, I have to use these two little buttons. The first one is when I do the training with the train set. And then once I built the model, I'm going to supply the test set here. So when I do this, I'm going to select the test set. But for now, I'm going to use the currently loaded data set, which is this one. Notice it's 60,000, right? So that's the train set. So this just tells it to use that data set to build the model. Notice also the label is not set correctly. So we have to go and look for it because it thinks it's the last one, but you have to tell it that it's the first one. Got it, guys? Making sense? Labels don't need to be the first one. They're wherever they are in the data set. You just have to find it. Okay, you just have to, like today, I had to select that label is the first one and the previous one is the last. All right, so now I'm going to train it, not with 0R, but with naive Bayes. Remember, here, I want to run naive Bayes first. Here, I want to run naive Bayes first because naive Bayes is faster. And so because this is now 60,000, now I have a good computer, I think, good laptop, so it should be fast. But still, I'm going to start with naive Bayes because it's the fastest. So I'm going to select naive Bayes over here. Got it. Use train set. Label is set. All right, we're ready to go. Click start. Look at the little bird. It's taking its time now. So it's thinking. Still not done. And naive Bayes is the fastest. So think about this, right? Still thinking. This is why when you do machine learning, you need a GPU box. NVIDIA graphics card, NVIDIA, what is it, RTX 2080 or the 30 something? Those are the ones. Just make sure that it's compatible with deep learning libraries like PyTorch and TensorFlow. But if you like this kind of thing, and you're a gamer, definitely worth the investment. All right, so let's see. 2080, isn't it 2080? I thought it was, or was it 2060? I have a 2080, I think. Okay, I don't know. What you have to do is, if it's an NVIDIA RTX 2060, let's say, you have to go in online with NVIDIA and read it to see if it's compatible with CUDA and machine learning, deep learning libraries. Okay, that's basically how that. I don't know about the 2060 offhand. All right, anyway, it's done, right? Took a while actually for the slowest. Let's make this bigger. So let's look at, now it's a balanced data set, which tells me that accuracy is reliable. Look, accuracy is 70%. What do you think? What do you think about a classifier that's 70% accurate? Is that good or bad for you? Guys?
Well, maybe it depends on what you're doing, but I don't think it's very accurate because that means 30% of the time it's wrong.
Yeah, exactly. That's a good answer. And that's why when we talk about the metrics in the next lecture, for instance, in cancer detection, do you want to build a classifier that detects cancer 70% of the time? Probably
You want it
not.
100%, ideally.
Mm-hmm. Exactly. So we'll get a feel for that next lecture when we talk about that. But today I kind of want to, instead of doing the lecture, I wanted you to see this, and then now you're clear as to why you want to understand these metrics a little bit better. All right, so there are 10 classes, as you can see. And then remember, the last one is the overall. So let's see precision. 86, 85, there's a 79 there, a 68, 42, 40, 49 for some of these, right? Recall, same, there's a few 42s. Remember, F measure is kind of a, if you can only look at one metric, we look at F measure. Let's see F measure. We've got a 39 in there for one of the classes. Overall, 68. So not ideal, right? If we look at the diagonal, look, but there's a lot of misclassifications. You see that? Because these should be zeros. Is this making sense, how you interpret the data and do the analysis? All right, good. Now, mind you guys, this is only the results on the train set. Now, what I'm saying here is I train on this data and then I evaluated on this data. That's cheating. This is only this won't fly in a competition, right? So this gives you a feel for what's going on. But now we have to do the really challenging part, which is applying this model that we just trained on the test set. And so now my intuition is that the results are going to be even worse on the test set. But I don't know, I may be wrong. So now let's try it. So I'm going to click supply test set over here. I'm going to click set, and I'm just going to say open file. I'm going to go to that test set CSVR, load it up. Make sure that the class is the correct one, which should be label, right? And I'm going to hit close. And so now I've loaded the test set. Now to apply the model to that test set, I need to go to the little here, the highlighted naive base, and I'm going to right click on it. And when I hit right click on it, there should be reevaluate model on current test set. Do you guys see that? And so what that means is the model that I just trained on the train set, now I'm going to evaluate on the test set. Let's see how it does. I'm going to click. It's going. Look at the bird. It's thinking. And it finished. All right, so let's take a look. Now this is more reliable results because this is on the test set. So actually it didn't do that bad. Accuracy is 69. If we look at the F measure overall, 69. You can see there's smaller numbers here because the test set is smaller, but the F measure overall is 69, and then, yeah, not so bad, not so bad. But let's take as a metric, F measure of 69. Still, it's not even 70, right? So we want to do better. So what would you recommend that we do? What do you guys recommend I do? What did I say about naive Bayes?
That's fast, but not as accurate.
Fast is not as accurate, so let's try another one.
We could use a different one. It might be a little slower, but it'll be slower, but it'll be more accurate.
Yeah, let's try, for instance,
Could we try known nearest neighbor?
yeah, let's try that one. All right, so I'm gonna select now IBK. That's KNN. Again, we have to train it, so remember to click this, use training set, right? Make sure the label is set correctly. Start. So it's currently training. Look at the little bird. Let's wait for it. Still thinking. See, this is not even like a multi-layer perceptron, right? Which would be extremely slow in this environment. Still going. So as you can see, one thing to motivate here is that, as I said, I wasn't kidding about NVIDIA GPUs, right? This data set has 60,000 samples, 784 features. That is a small data set. Okay, nowadays, real data sets have 2 million samples and thousands of features. So when we do this kind of thing, we actually want to do it with more efficient code. That's why this justifies, using NumPy, using other libraries, Keras that we will look at later in the semester, and having a parallel architecture with GPUs, for instance. So it's still going, and it's only training, although training should be longer. So I think I'll just do this one, and then I'll let you guys play with these. So what we're gonna do is, I think, I don't want to mix like this with the code. So we'll look at loading a CSV into Python on Monday. And instead, I'm just going to make this, your homework for this week will just be this, okay? Running 5 algorithms, doing basically what I'm doing, but with 5 algorithms on the MNIST data set. And then you guys can give me your results. Does that make sense? So you know how to do it. It's just, it'll take a while. And I'll indicate the algorithms. And this is taking a long time. I wish I had picked decision trees instead. Yeah, I think we're back in person on Monday. That's what I've been told. Let's see. Somebody's asking me result is in the screenshot of the class. Yeah, so you need to provide. So yeah, for the homework assignment, you will need to create a report, and the report, you need to provide an analysis, right? So it's data science, right? So you need to. It's not just like showing me code and here it is. You gotta show your code, but then run it, and then show results and interpret the results and provide conclusions, if that makes sense. Okay, so I'll create an assignment in a sec, and I'll just say something like, perform the analysis on the MNIST data set, train 5 models, and then indicate which ones are the best and why. Make sense? All right, so it's evaluating on training data, process 5,000 instances. This is out of 60,000, so that's going to take a very long time. All right, so I'm going to stop this one. There should be a stop button here. Yeah, stop. I'm going to pick decision trees. Maybe that one will be a little bit faster. 48. Let's see. Let's just give this a second. And if that's too slow also, I'll just leave it for you guys to do on your homework assignment. So you can see, again, WEKA is great, but unfortunately it takes a little while. For a data set, so that's why I said, honestly, you have to, just for a subsample of the data to kind of get a quick look, wait some hours. If you have millions of records, unless WEKA has some GPU adjustments, it will be impossible for you to get results. So you can see how the world has changed, right? Imagine 10, 15 years ago, this was the tool, if you will. So you couldn't really solve that many problems, right? Today, we have all this new hardware and techniques, and so we're able to solve the same algorithms, really. It hasn't, one of the big things in deep learning hasn't been that they've necessarily invented all these algorithms that are new, but that the computing power has just caught up with them. If you think about it, the initial perceptron, which we will talk about in the second half of the semester, was invented in the 1950s. And it's like the granddaddy of deep learning today. But in the 1950s, they didn't really even, they were just inventing the transistor, right? So think about that, how that works. It's only the hardware is catching up to the theory now. So imagine when you guys, in 10 years or so, you don't even have to wait that long, I don't think. Imagine the computing power and then what we'll be able to do. So it's pretty exciting, I think. All right, I think decision trees is actually really slow. So let's stop it. I'll let you guys do it, okay? Might take you a day or two. It'll eventually finish. It just takes a while. The last thing I want to show you of WEKA is this idea of select attributes. I really like this also. So the main premise is that you have a classification problem of numbers. You have 700 features, and you just want to determine what are the best features in your problem. So what you can do is you can go to select attributes, and then here you're just going to decide what you want to do. So go to search method, click choose, click ranker, and basically what ranker means is that it's going to rank all 784 features based on the ones that are more useful to your classification problem. Click yes. Now, the method that it chooses by default is information gain. That's a good one. There are other alternatives. If we choose over here, there's there's a few other ones in there that we can select, but let's just stay with information gain, okay? Close. And now what I'm gonna do, again, use the full train set. Make sure you select the label and now hit start. This should be faster. And it's just going to print out a list of the features. So out of the 785 or 784 really, because it doesn't use the class for this, it'll tell me which ones are the best. Do you guys understand this concept? And there it is. As you can see, it actually says, you know what? All the ones that have a 0 value are basically not useful to the problem. Look at how many are not useful. And then the ones that have a value here, those are useful. And then the most important ones are, because there's a lot of them here, these, like these features are the most important. Now, my intuition would be that these are probably the pixels somewhere in the center of the image. And why is that? Well, if you think about it, because we were writing the images kind of in the center. You see that? So it's probably, those are the pixels that it's identifying as the most important because they're somewhere in the middle. This is really useful. If we, for instance, do Iris, think about Iris, right? And I'm going to load Iris. And I just want to give you a scenario as to when something like this would be useful. So let's load Iris data set over here, right? And I have Iris loaded now, and I go to select attribute, and I need to select the class, species, use full training set, rank, or information gain, hit start. Notice Iris is tiny, so it did it fast. Notice that it tells me that really, to identify the plants, the thing that you need to look at is the petal length, followed by the petal width. You can almost ignore the sepals, and you would do kind of okay. Obviously, the more data you lose, the worse your performance. But let's say that you have to hire a botanist, 2 botanists, one to go in and look at the petals, and one to look at the sepals, whatever that is. So, but your budget does not allow you to hire 2 botanists. You can only hire 1, or whatever, plant people. So you can only hire 1. So who do you hire? The expert in petals or the expert in sepals? According to this. Yeah, exactly. You pick the one. According to the data, the petal specialist is the one because that will help your model work better. And so that's how you do it. So this is actually really useful for that, okay? For getting insights about your data. All right, so anyway, that's it. So hopefully this made sense. Are there any questions before we talk about the homework? All right. So this is a long topic, as you know, so let's go back to Brightspace for a sec. All right, so you should be seeing Brightspace. So this week, we covered KNN, and I've created the assignment for KNN. No, I haven't, because this is the old one, right, from 2021. Implement the KNN algorithm as discussed, create some data, train, test, and balance. Yeah, I've changed this to now use Iris. So, but I didn't show you how to load the data. So let's hold off on this one. I haven't created an assignment link. This is last year's. So basically there's nothing for you to submit. So that's good. So instead, what we're gonna do is, because today I only had time to cover WEKA. Your homework will just be on WEKA. Now, if you notice, I didn't cover this. I'll cover this in the lecture on Monday. This is pretty important to understand the differences between the metrics. And then I will cover the main ML as well on Monday, which will be about loading the data and a few other things. And then here you can see there's a WEKA homework. So this one certainly is what I'm going to do today. So I demoed. So let's see. Using WEKA, analyze the Iris and MNIST data sets provided in the course website. Perform classification with several classifiers, IBK, naive Bayes, decision tree. All right, so that's 1, 2, 3, 4. I'll add one more, and feature ranking. Okay, perfect. So this is exactly what, I'll just modify this a little bit, and that should be your homework. Here, because this is last year's, I'm just going to delete it. It copied this year. I don't know why. All right, let me I'd rather create a Word document for this. So let me just create this. All right, let me share the document. All right, so this will be the document. So this is your ITS 365 homework. And this is WEKA. All right, so basically, using WEKA, analyze the MNIST. Let's just do MNIST because I did Iris. Analyze the MNIST data sets provided in the course website at the link. Perform classification with several classifiers, IBK, naive Bayes, decision trees. Let's do random forest. And you can try some additional ones if you want, and the multi-layer perceptron. Just be prepared probably to run this overnight. Okay, this is a long one. And feature ranking. So perform classification with several classifiers and feature ranking. And then report your results and indicate which one is the best. Is this clear enough, guys? For your homework?
So all I got to do is run the different data sets and train sets in the WEKA and show what it does.
With the
Using those
different
different. Yeah, we got to use. Do we use nearest neighbor too? Doesn't say to use nearest neighbor, so I don't think so.
What's IBK?
Oh, okay.
Got it?
Gotcha.
All right, so let's add this then to the bright space. Okay, table of contents. All right, performance metrics. So I'm going to add a new assignment. This is going to be homework. WEKA. That should be clear enough. And this will be due. So today's the 26th. So it'll be due on the 2nd by 10 p.m. It'll open today. And it'll close on the 5th. Complete the WEKA problems in the attached document as discussed in class. Fair enough? All right, great. So I'm going to save this and you have your assignment. So go ahead and work on that. Then on Monday, we will, on Monday, we will circle back to the slides and then go back to Python. I'm done with WEKA. I'm done with my WEKA demo. All I have left is the experimenter. So if I do this, I just, experimenter, right? This I'll come back to in another lecture later in the semester, but after we've covered the t-test probably. So we'll come back to that. All right. Okay, guys, so that's it for today. So I'm going to stop sharing. I'm going to stop the recording now.